Welcome to this course on environmental biotechnology. I'm Mark Vloosrecht, a professor in the Department of Biotechnology at Delft University of Technology. In this course, we'll explore the core principles of environmental biotechnology and showcase real-world applications that contribute to a cleaner, more sustainable world. Environmental biotechnology harnesses microorganisms to tackle environmental challenges, playing a vital role in sustainable development. Environmental biotechnology uses microbial processes to remove pollutants from water, gases, or soils and potentially convert these pollutants to useful products. In natural ecosystems, microorganisms drive the cycle of essential elements like carbon, nitrogen, phosphorus, and sulfur, enabling life. For example, bacteria and plants convert simple molecules like CO2 and ammonia into complex organic compounds. After organisms die, microbes break down these compounds back into simpler forms, sustaining the elemental cycles. However, human activities disrupt these natural cycles through large-scale conversions of these elements, for instance, production of ammonia in industrial processes. Environmental biotechnology counters these impacts through applications like wastewater treatment, soil remediation, bioenergy production from organic waste, and resource recovery. Human activities significantly disrupt global elemental cycles. Naturally, nitrogen-fixing bacteria convert atmospheric nitrogen into ammonia. However, the industrial Haber-Bosch process now rivals this natural fixation, producing vast amounts of ammonia. In wastewater treatment, we convert this excess ammonia back into nitrogen gas, or recover it to prevent eutrophication, a process which excessively nutrients cause algae blooms, harming aquatic ecosystems. Microorganisms are remarkably versatile, thriving in conditions far beyond those suitable for plants or animals. While visible life relies on oxygen and specific energy sources like sunlight or organic carbon, microbes can survive in extreme environments, acidic, alkaline, hot, or cold, as long as liquid water is present. They harness energy from diverse redox reactions, not just oxygen-based ones, allowing them to grow in unique ecological niches and on unique substrates. This microbial diversity is key to restoring disrupted elemental cycles. Human activities release this carbon, nitrogen, sulfur, and other elements mined from geological deposits into waste or wastewater in diluted forms. Microbes excel at capturing and recycling these elements, helping us close these cycles and mitigate environmental pollution. This tree of life illustrates the diversity of life on Earth, divided into three domains: bacteria, archaea, and eukaryotes. Within the eukaryotes, we find the visible forms of life, though you can already appreciate that most life forms are microscopic because archaea and bacteria can only be seen under a microscope. Plants represents a small branch of eukaryotes, yet their diversity is vast, hinting at the even greater diversity among bacteria. The same is true for animals. They form another small branch of the eukaryotes. Yet, within that branch, there is already a huge diversity, giving a sense of how immense bacterial diversity must be. And within the animal branch, humans or Homo sapiens form an even smaller branch than the metazoan or the animals, yet still displays a large diversity. In environmental biotechnology, we primarily use prokaryotes, bacteria and archaea. While only about 9,000 species are described, an estimated 15 million exist, offering vast potential for applications like wastewater treatment and resource recovery. Environmental biotechnology exploits the microbial metabolic diversity. Unlike humans, who rely on oxygen to oxidize glucose for energy, bacteria can breathe compounds like sulfate, nitrate, or even pollutants like trichloroethylene. All life depends on redox reactions, but bacteria can use a wide range, converting harmful pollutants into harmless, manageable products, such as turning organic carbon into CO2 and water, or trichloroethylene in hydrochloric acid and ethene. In applications like wastewater treatment and soil remediation, environmental biotechnology transforms waste into harmless products, such as oxidizing organic carbon into CO2 and water, helping to close elemental cycles. Beyond waste treatment, environmental biotechnology works on converting organic waste into valuable products. Bacteria break down waste into volatile fatty acids, which can be transformed into bioplastics, methane for energy, or long-chain fatty acids for industrial use. This presentation has introduced the concept of environmental biotechnology, setting the stage for our course. The course is divided into 4 modules. This first module on basics covers the microbiology and engineering principles essential for understanding environmental biotechnology. The second module is about the elemental cycles, exploring microbial processes in nature and their potential. The third module is on applications, examining how we apply these processes in real-world solutions. The last, fourth module is on tools, introducing methods to study complex microbial systems and their role in wastewater treatment. We look forward to diving deeper into these topics with you. Through these modules, the course aims to bridge microbiology and engineering, thereby providing a comprehensive understanding of environmental biotechnology.